In the previous course, we've discussed solving a linear system Ax equals b using elementary row reductions. However, just staring at the abstract equation might make you wonder, why can't we just divide by a? It feels so tempting. But once we write it down, this notation does not really help us compute anything. What would this fraction be? In fact, once we recall that some systems Ax equals b have infinitely many solutions, and others have none at all, or just one, we conclude that b over a is apparently not a fraction that we can just compute. The notation is not helpful, not meaningful, and just plain wrong. We cannot divide by a matrix. However, for some matrices, we can define something related to divisions. Some matrices have a so-called inverse. Consider a square matrix A. A matrix C is an inverse for A if AC is equal to the identity matrix and CA is also equal to the identity matrix. We ask for both identities since order can affect the outcome of a matrix product. A matrix which has an inverse is called invertible. A square matrix without an inverse is called singular. Actually, computing an inverse will be postponed to the next video. For now, we are going to look at the abstract concept of an inverse. So far, I've been careful to talk about an inverse. But, in fact, a matrix cannot have multiple distinct inverses. Suppose that C and D are both inverses for a matrix A. That is, they both satisfy the two requirements. We write C equals C times identity. But the identity matrix is equal to AD, so we get CAD. We are allowed to compute CA first though. And by the properties of inverses, CA is the identity matrix again. So we end up with ID, which is just D. And hence, C apparently equals D. So for an invertible matrix, we can talk about its unique inverse. We denote it by A to the power -1. For example, the matrix A over here has an inverse as shown on the slide, since both products of these matrices are equal to the 2 by 2 identity matrix. We'll get back to this example later. Once we have an inverse matrix for A, solving a system Ax equals b becomes quite straightforward. We can immediately write down a solution. The vector u equals A inverse b. Just plug it into our equation to verify. A times u equals A times A inverse b. Change the brackets to compute the product of A and A inverse first. And that's the identity matrix. Hence, we end up with b. Moreover, the vector u equals A inverse b is in fact the only solution of this system. If v is some other solution, then A times v equals b. Left multiplication by A inverse shows that A inverse AV equals A inverse b. But this simplifies to IV equals A inverse b, and hence v equals A inverse b, which is just our vector u. So apparently this is the only possible solution of this system. So if A is invertible, any system Ax equals b has one unique solution. Neat! Returning to our example, we can now immediately solve the system Ax equals 410. Its unique solution is A inverse multiplied by the vector 410, which is the vector 2, 1. This little exercise in matrix vector multiplication can be regarded in two ways. On the one hand, a system Ax equals b, where A is invertible with known inverse, is very easy to solve. It has the unique solution A inverse b. And this formula holds for any vector b of appropriate shape. Very convenient. On the other hand, this convenience puts quite some restrictions on A. The system Ax equals b is apparently consistent for all b. Therefore, there is no row of zeros in an echelon form of A. That is, the matrix A must have a pivot position in every row. On the other hand, note that the solutions to all these systems Ax equals b are unique. So there are no free variables, and hence, the matrix A must have a pivot position in every column. We see that the reduced echelon form of A has a pivot position in every row and every column, and hence it must be equal to the identity matrix. This means that any matrix whose reduced echelon form is not the identity matrix cannot be invertible. So, non-square matrices are not invertible, to give an immediate example. And this square 2 by 2 matrix is not invertible either. This matrix is not row equivalent to the identity. This third example is row equivalent to the identity. It could be invertible. We'll get back to this later in the course. So if A is invertible, can we then divide by A? No. Even for invertible matrices, the answer is still a definite no. Let us return to our example and introduce a matrix B. Can we interpret the fraction B over A in a sensible way? Since A is invertible, we could consider A inverse B as a possible meaning for this fraction. But there's another candidate, B in A inverse. And this is an entirely different matrix. The key issue here is order matters in matrix multiplication. An expression like B over A does not keep track of order, and therefore should not be used. Instead, multiplication by inverse matrices allows us to perform division-related computations in a way that respects the peculiarities of matrix products. In the next video, we'll move on to the elephant in the room. How do we actually compute an inverse matrix, if it exists at all?